Hey, welcome to Planck's Quantum Hypothesis for Physics 30. We're actually going to start with a video within a video, so let's go to that first.
As the 1800s came to a close, the scientific study of things no one could see was the new hot thing. It was the pre-quantum era, and the race was on to uncover the mysteries of energy, light, and heat. Everyone knows that if you stick something into a furnace and heat it up, it will begin to glow red. It doesn't matter what you stick inside. Glass, coal, that ridiculous ceramic dog your aunt gave you for your birthday. When it reaches a given temperature, it will always glow the same color, progressing through each phase of the color spectrum as it heats up, going from red to yellow to white to blue to ultraviolet and beyond. If heat were only allowed to escape from one small hole, it should be possible to accurately measure color frequency and intensity. Classical physicists of the late 19th century, like Lord Rayleigh and James Jeans, spent a considerable amount of time studying this concept known as black body radiation.
Hey, Rayleigh, throw another particle in there.
Throwing! All right, Jeans, hit it!
Hitting!
Oh, that's hot!
Wow, that was intense. I'd say at least 1900 degrees Celsius.
Dump a lot of particles inside a black body, heat it up, and the box will eventually fill up, limiting its maximum intensity to a finite and safe number.
Jeans, how about we throw a few electromagnetic waves into the old black body?
Why not? There's no limit for those. Brilliant!
Switch over to electromagnetic waves, which have no mass and take up no space, and theoretically there is no limit to their intensity and radiation. The shorter the wavelength, the more room you have for additional waves. According to classical physics, you could keep cramming that box full of waves and always find room for more.
Turn up the heat!
Turn on the heat, and every one of those waves would start vibrating, driving the black body's color frequency well beyond the ultraviolet, and its radiation to infinity, resulting in
Riley! Oh, hot, 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 hot!
But this was obviously not the case.
Hey, Jeans, shouldn't your eyes be melting right about now?
Why didn't heated materials behave the way classical physics said they should? Why doesn't our own fireplace emit so much radiation as to blind anyone who sat in front of it?
Ow, my eyes!
Max Planck!
Physicist Max Planck did not come onto the scene intending to create a whole new branch of science. He liked classical physics. He was simply trying to figure out why black body equations didn't match black body reality. In an imaginative leap, Planck envisioned a collection of electric oscillators inside the walls of the black body that vibrated faster and faster as the temperature inside the furnace increased, emitting energy the entire time. The higher the frequency, the more energy the oscillators emitted, which once again, according to classical physics, dictated catastrophic results.
Nice face!
This is going to hurt in the morning. I am repeatedly confronted with reliable data that cannot be explained by any accepted theory.
Unable to make the numbers work any other way, Planck turned to Maxwell's energy distribution for particles. What if energy came not in an unbroken continuous wave, but in a series of discrete energy chunks? When he plugged it into his equation,
Energy equals a constant h times the frequency of the light.
it worked.
Oh, joy!
Oscillators did not emit energy in a continuous range. Instead, energy was emitted via discontinuous and indivisible units, which Planck called
Energy quanta!
For any given temperature, the quantum of energy is given by this formula, where F is the frequency and H is known as
Planck's constant! Max Planck!
The quantum was born, And Planck's so-called electric oscillators were actually primitive renditions of what would eventually become known as the atom.
So what is Planck's constant? Planck's constant is 6.63 times 10 to the negative 34 joule seconds. Okay. We symbolize that with the letter H, and this is an incredibly small number. Now we also have another value here of 4.14 times 10 to the negative 15, but instead of joules, we've just used an electron volts for energy. This is a unit of energy, and joules is also a unit of energy. And so we've just got the two different versions, depending on whether you're measuring your energy in electron volts or joules. So the significance of Planck's constant is basically that energy is quantized, just like charge. So energy can only exist within specific amounts. It does not build up like a wave, but actually exists as a particle in a sense that you can only have one or two or three or four of these little bundles of energy. And it's just simply a quanta of it. So what does this mean in a gravitational potential energy store? Well, if energy can only be quantized and potential energy is stored within the heights using the formula EP is equal to mgh, ultimately what that means is that objects can only exist at specific heights. Does it mean with the kinetic energy store? Well, that equation, EK is equal to 1/2 mv squared, means that objects can only move at specific speeds. What about an elastic potential energy store? 1/2 kx squared. Well, that means that objects such as springs can only be stretched to very specific amounts and nothing in between. What does it mean for a radiation pathway? Well, that means the radiation comes off in distinct little bundles, and so even though you have several of these little bundles, the amount of individual energies do not add up, and therefore people don't fry their faces off. So if we think about it, we've got that electromagnetic wave, but instead of a single wave coming at you, they are distinct little bundles that are moving along. So the formula Max Planck generated eventually was E is equal to hf, where this is Planck's constant. And F is simply the frequency. Now for photons, we can also change it up like this, where we use that universal wave equation, where c is the speed of light, and substitute that in for frequency. Another version we're going to look at here is we substitute in frequency for 1 over the period. So let's take a look at this first example here. We've got a 30-gram mass vibrating at the end of a vertical spring with this spring constant of 0.22 newtons per meter. What's the difference between allowed energy values? Well, E is equal to hf, or again, substituting in 1 over t for that. So what we need is to know the period of this vibrating mass. 2 pi square root m over k. 2 pi, the mass is 0.3030 kilograms divided by 0.22 newtons per meter, as already described, which makes the period 2.32 seconds. Now, going back to the equation that this is mostly about, we've got the energy is equal to Planck's constant 6.63 times 10 to the negative 34 joule seconds divided by 2.32 seconds. Notice the seconds cancels out. And so the energy is, to two digits, 2.9 times 10 to the negative 34 joules. Double check my work there, make sure that I am in fact calculating that right. And notice here that that again is an extremely small number. But if we think about as this object is vibrating back and forth, it will only be allowed to stretch specific amounts, and thus each one of those is an extremely small amount, too difficult for us to distinguish within our perception of reality. So I would like you to try this next one. What is the quanta or difference in allowed energies of a 0.5 meter long pendulum on Earth? Again, pause the video, give this a try, and let's see how you do. So again, E is equal to HF, replacing F with 1 over T and finding the period of this pendulum here on Earth. 1.418 seconds using the pendulum formula. Plugging that in using Planck's constant, you find 4.67 times 10 to the negative 34 joules. Again, a very small amount. However, that's going to be dictating the fact that this can only be moving at certain speeds or even existing at certain heights. So let's bring this back to the electromagnetic radiation. What is the energy of a single photon on a keychain laser pointer? We've been given the wavelength, and I just pulled this off of the label. So E is equal to hc over wavelength. So we take Planck's constant, 6.63 times 10 to the negative 34. I'm not going to put in the units here, but we know they do check out. Plugging in our numbers, and that means that each photon, each little tiny bundle of energy, contains only 2.93 times 10 to the negative 19 joules. Now, obviously, this is going to be releasing lots of these. However, each individual one has this. So keeping that number in mind from the previous question, 2.93 times 10 to the negative 19 joules. In this question, we've got a 0.5 watt bulb used to produce light. How many photons are emitted each second? Well, power is equal to work over time. We've got a power rating of 0.5 watts. And knowing that work is the amount of energy means that power multiplied by time is the amount of energy that this is going to be giving off. Now, we're assuming 100% efficiency, meaning we're assuming every single one of these is going to a photon of 680 nanometers. Okay, power being 0.5 watts, time being 1 second for the energy, that means the total amount of energy is 0.5 joules that this is giving off each and every single second. Now we know each photon is 2.93 times 10 to the negative 19. So we're going to take the total amount of energy, divide that by the energy of each individual photon, and that gets us 1.71 times 10 to the 18 photons that are released each and every single second. That's a lot of photons. Okay, what I'd like you to do is to give this one a try. Find the energy of one photon of now radio, which is 102.3 megahertz. Remember, mega is just times 10 to the 6. Pause the video and let's see how you do. Okay, welcome back. E is equal to hf. We've got the frequency. Planck's constant is the same. And so each photon of now radio is 6.78 times 10 to the negative 26 joules. And remember, because it's a radio wave, these things are going to be extremely long in meters or potentially even kilometers. Using the universal wave equation, we could figure that out, but we're not going to right now. Give this one a try. A UV light gives off from a 600 watt bulb for 1 minute. How many photons is it releasing, given that the wavelength of light given off is 2 times 10 to the negative 7? Again, pause the video and let's see how you do. Okay, so if you got 3.62 times 10 to the 22 photons, great job. First thing again, what we did is we figure out the energy of each photon using the formula this unit is basically about, starring Planck's constant. Second, we find the total amount of energy that is being produced, or that is given off by this lamp each and every single minute. Now, 1 and 2 steps could be done either way, because ultimately what's happening is you're just taking the total amount of energy divided by the energy of each individual photon to find out the number of photons. Okay, so I hope that helps. If you do have any questions, please let me know.